Hi, welcome back to Unit 7. This is topic 7.3. I cut the last video short to kind of preview this. So here we're going to talk about representing and analyzing simple harmonic motion. So the new curriculum will have the added idea of that simple harmonic motion can be represented by a sine or cosine curve. The dependence will be on where do you start taking your data. So for an object exhibiting simple harmonic motion, the displacement of the object measured from its equilibrium position can be represented by one of two equations. So x equals a cosine 2 pi ft. Okay, so it's more like x of t, or x of t equals a sine 2 pi ft. So there's a lot going on here, but your variables, right, your independent and dependent variables are x and t. Okay, now the question shows up as when do I use cosine, when do I use sine? So it all depends on when you start taking your data. If you start your data when x equals 0, you will use sine, right? Because if I plug in t equals 0, if I plug in 0 for t, then I get sine of 0. Well, that's just going to be 0, okay? If you start at x equals a, where a is the maximum amplitude, then you would use cosine. The majority of the time, you're going to use cosine, right? Yes, I know if I look over here in the pictures or the graphs that I've shown for displacement, velocity, and acceleration, the displacement graph starts at 0. So this would be actually represented by a sine curve, okay? But in this case, most cases you'll start with cosine. There are minimum, maximum, and zeros for the displacement, velocity, and acceleration, okay? These are going to be special features of the harmonic motion. Something to know that changing amplitude of the system will not change the period of that system. That just means it goes back and forth higher, or it goes up and down with a greater value. And then properties of simple harmonic motion can be determined and analyzed using graphical representation. So that's what we have over here. So if I'm looking at the pictures I have, not necessarily the ones that we would probably use, okay? X equals 0, x equals 0, right? Now, something you'll note is as x equals 0, you'll see that your velocity tends to be at a maximum, okay? And then if you go all the way down to the acceleration, your acceleration would be 0. And you'll see that the acceleration function is kind of the opposite, right? The negative of the displacement function. Because as you go through, if you were to take AP Physics C, you would derive the rest of these equations, right? And so V is negative 2 pi Fa sine 2 pi Ft, right? And then if you were to take the acceleration, you end up with negative 4 pi squared F squared A, sorry, I mean, the parentheses already, okay, cosine 2 pi Ft. And remember, omega is 2 pi F. So if you want to shorten what that would look like, you could just write omegas. And so you end up with like maximum X max is A, V max is omega A max is omega squared A. Okay, and that's where all of this kind of comes into play. All right, so let's look at an example problem. All right, so we're given the function of simple harmonic motion is d equals negative 4 cosine pi t. We're going to find A, the maximum displacement, the frequency of the period, the value of d when t equals 10, and the least positive value for t for which d equals 0. Okay, so A is very simple. Max displacement, well, that's just going to be our amplitude, and that's going to be 4 meters. Okay, that's what this number is right here. Okay, in fact, you could say -4, but really you just have to put 4. Okay, so what that means is if I have a mass spring oscillator, I'm starting on the negative side of it versus starting on the positive side of it. Okay, part B, the frequency. Well, pi, let's do this. So we know omega is 2 pi f, but that's what this represents. So it's a pi equals 2 pi f. Okay, and I can do some cancel out here. Pi, and so I get 1 equals 2f. So f is going to be 0.5 hertz. Okay, and I think I failed to mention this way back in the first video, or at least, oh no, in this, we can talk about in this video. So the unit of frequency is hertz, and hertz really is seconds to the -1. Okay. Part C says find the period. So we know frequency and period have an inverse relationship. Okay. And so what we're going to say is t equals 1 over f. Well, that's going to be t equals 1 divided by 0.5, which is 2 seconds. And remember, period is a specific time, so the unit would be seconds. All right, next part, the value of d when t equals 10. And so we're just going to simply play, okay, d of 10 equals -4 cosine pi times 10. Typically, you would keep your calculator in degrees, but this is a case where you would need to make sure you're in radians. So I'm going to make sure I'm in radians before I do this calculation. So we have -4 cosine 10 pi, and we find that 10 seconds, the displacement is -4. That's okay. That should be that should be easy because it repeats every 2 seconds. So that means I have 5 complete cycles. So yes, it should return back to my original position. So this is part D. And part E is a little bit, we've got to do a little bit of fun solving here. So we want to find what is the smallest value for t when d equals 0. So we're going to say d0 equals -4 cosine pi t. All right. Well, this, if we divide by -4, we get 0. So 0 equals cosine pi t. And so then we would simply take the inverse cosine or arc cosine. So you end up with cosine -1 to -1 0 of pi t. Well, cosine of -1 0 is going to be 0. Okay. Hold on. Let me. Sorry. 0. This is going to be pi over 2 equals pi t. Right, so the inverse cosine is 0. When is cosine 0? Well, at pi over 2 at 90 degrees. Cancel, cancel, and it's going to be t equals at 0.5 seconds. So if I'm plotting this, right, my function, I'm going to have something that looks like this, right? And then this is where I start. Okay, sorry for the bad picture, but when is the smallest value when we're at with the least positive value is at half a second, right? And so this repeats itself every so many seconds. And so the smallest positive value, right as you hit that 0 point, right, at half a second. Okay, so this topic, not new in terms of how do we analyze it, but it is new in terms of using that cosine function, the sine cosine functions to represent the motion. Okay, and then we're going to wrap up Unit 7 when we look at the energy of simple harmonic motion.